each case appears, that the statement will be true. So in each case I have to prove what I need to get 8m plus 1. So case 1, case even, case 2, case odd. And there is no third case, so generally these cases need always to exhaust all the options. So these are the only two cases, there's no third case. And then what do? Well, k is even. Why would our number be even? Then just again, k is even. That means that k is some number 2l's. So our x squared will be 4 times 4l squared, I plug it in, plus 2l plus 1. I can factor another 2 and get 8 times 2l squared plus l plus 1, which is 8m plus 1, where m is obviously 2l squared plus l. So this is checked. That's good. If k is odd, the same thing, just a little different algebra. I need to close with, say, that case as well. So when we plug it in, k squared would be 4 from outside. Then that k squared plus k would be 4l squared plus 4l plus 1 plus 12. Heavier algebra, but nothing bad. Plus 1. Again, because 1 and 1 is 2, I can obviously factor out 2 again, and I get the little algebra 8 times 2l squared plus 3l plus 1 plus 1. I think I'm correct about that, rushing. So if I call this m, and that's an integer, I have 8m plus 1. That's checked. So once again, just verbally saying, if you have exhaustive cases, so that there's no third or fourth case, or there are no other cases except those that you analyzed, and if you prove the statement in each case individually, then you have the full proof. And that's the statement that we actually expressed. If we have what? I'll just write it a little different than in the notes, but that's also correct. If you show that A1 implies B, that's your first case. You show A2 implies B, AN, as many cases as you want, that each of them implies B, but also you show that they are exhausted. That means that one of them has to show up. Then that's the same as you prove B. And that's exactly what we applied here, just on 2 cases. First assumption implies B. Second assumption, one of them must appear. B is true itself. And then at the end of this section, we want to just illustrate some of these statements. Methodology of proofs on rational numbers. So generally rational numbers are defined. So what is a rational number? So definition, a rational number, so Q is a rational number if Q is basically fraction, m over n, where m and n are both integers. And what else is very important? That n is not 0. Sometimes we also say that n is positive on its own, but generally we just say n is not 0. So if you can find those witnesses m and n so that you write your number as a fraction, then you are saying that q is a rational number. And then what? We have operations about these rational numbers. So how do we define operations? If you have m over n, let's say, I better use the same letters as in the notes. K over L. By definition, this is not proof, you just cross multiply as you know, ml plus kn. And then it's important that since these two numbers are both different from 0, and L is also different from 0, so you don't need to worry about it, if N and L on its own are different. Then you define how you multiply two numbers. And there are and subtract, and how do you divide it, and so on. And then, here we mentioned one very important principle here that you used in algebra, and this is called zero product principle. That's about integers here, and that's the one that I called here. If those two individually are not zero, and L is not also not zero, so I wanted here to emphasize that important theorem about integers. It's called zero product principle. Maybe it's better to use the black marker. Zero product principle says, so for m and n in integers, if product of two integers is 0, then one of them must be 0. And that's principle that you use all the time in algebra when you solve equations, this or that, but just it's good to have it here explicitly stated if you forgot it or you never saw it before, because this is a very important principle for mathematics, and that's exactly what we used here. If this denominator is correct, not 0, and this denominator is correct, then this one is also correct. Actually, the way I called it, I said the following: n different from 0 and L different from 0 imply that n L is different from 0. If you compare those two, I hope by now you already recognize that they are the same thing. This is basically contraposition. Because we took negation of the consequence and used their Morgan, so they become negated and or became n, and this guy is just negated and we reverse them. So generally, this zero product principle is very often used both ways. And for example, I just showed you here, how do we show that A plus B, so for example, prove, for example. Prove that for every two rational numbers, A plus B equals B plus A. That's commutative law for rational numbers, and you are already familiar with that law, you've been using it during your algebra. Here we want to see, can we prove that property using the definition that we had? And generally, here's what you do. A plus B, here's proof. So if A and B are rational by definition, that means they are both fractions. So let's say A is m over n, and B is k over L, and then L are different from 0. And then how much is A plus B by definition? Definition says cross multiply and add them up, so it would be ML plus Kn over NL. I'm doing it exactly the way they are written. I'm not reordering them or anything. I'm doing it the way computers do it. So they just read, scan, and they plug it in, and they don't have any knowledge on that. So what about B plus A? Now, that's now K over L first, plus M over N. When I cross multiply, I get Kn plus, how does the definition say who comes first up? So plus ML over L. So I open the both things according to definition, and my question is, are these two things equal? And the answer is yes, they are equal. Let's squeeze in here the last sentence. They are equal because NL equals ln y dat, because this is commutative law for integers. And the same way, ML plus Kn is the same as Kn plus ML. Again, commutative law for integers and multiplication. This is commutative law for integers and addition. So since numerators are equal, denominators are equal, according to equality definition between two rational numbers, they are equal. So basically all these problems that you have in the homework and that might appear on the exam, whenever a statement says, prove that for rational numbers, then you immediately write them as fractions, call the definition, and then see, using properties of integers, how could you make a conclusion about your rational numbers. That's first observation. The second one is, or let me give you one more example. Sorry, just how do you disprove something about rational numbers? You can find that in your homework list. For example, someone says, example, prove or disprove that if I have two rational m over n plus k over l equals m plus k over n plus l. So prove or disprove. So generally what? This is what we see very often in very low level algebra classes, where people make this error and they add up fractions, just adding numerators, adding denominators, and then you want to tell them that actually that's not a valid law of algebra, that they cannot apply that law. So basically, you cannot prove it because this is not correct. What we want to hear is to disprove it. Because basically, even if you don't say, this means for every m, n, k, l, when there's a law, you are assuming always universal version of the law. So this is what someone who thinks that this is a good law would think, that whenever I have two fractions, no matter who's up and down, I can just add numerators and denominators. How are we gonna disprove that? Then we'll just choose. So find the counterexample. So let's say 2 over 1 plus 1 over 2, and I'll ask, is that equal to 3 over 3? Because when you add, you get 3 over 3. Obviously, on the left side, we get 2.5 or 2.5, and on the right side, we get 1. Obviously, this is not true, this is false. So that shows that a rule is not valid, that's not how rational numbers or fractions behave, and that's what it is. So to disprove a law, so-called law, you just find a counterexample where that rule doesn't work. The same way, for example, when you want to convince someone, it's not about rational numbers. Example, when people say a plus b squared equals a squared plus b squared, is that a valid law? Then you just take an example and say a equals 1, b equals 1. When you plug it in, you get 1 plus 1 squared equals 1 squared plus 1 squared. 1 and 1 is 2, squared is 4, equals 1 and 1 is 2. Obviously, this is not true, this is not true. And you provide a counterexample that this is not a valid law of algebra, and this is again counterexample. It's false. That was it. Thank you.